Well, thank you, everybody. Thank you so much for joining us for our June monthly meeting. My name is Alexander Gard-Murray. I'm the Executive Director of Passive House, Massachusetts. And before I introduce our terrific speaker, I just want to say a few quick words about our sponsor, the MassSave program. So MassSave, through their Passive House and All-Electric Homes Training and Workforce Development Program, provides robust incentives for Passive House building. It's funded by a coalition of the state's utilities. And the incentives include single-family homes starting at $25,000, going up to $40,000 for a 4-unit home. And for multifamily homes, the incentives are $3,750 per unit, plus extra money for modeling and feasibility studies. And I recommend that if you're doing a project that's going to use these incentives, one, you should do a project that uses these incentives, and two, you should reach out early. For the multifamily incentives, you reach out to multifhr@icf.com, and they'll help you get on the right path. There are also training incentives. You can ask about them at passivehousetrainingma@icf.com, or you can contact us at phmass.org, and we'd be excited to help you take advantage of this terrific program. So I couldn't be more excited about tonight's presentation. I've seen another version of it, so I know how powerful and thought-provoking it is, and that's why we're so excited to get it here at PH Mass as well. And I just wanted to say, I've been in PH Mass now for about 1.5 years, and it has been one of the pleasures of that work to work with Paul, to work with Ian, and the whole energy efficiency team at DOER. Sometimes I think bureaucrats can get a bad rap, and not always undeserved, right? But I think this team, DOER, the energy efficiency team in particular, is, I think, really defying those stereotypes. There's a really forward-thinking spirit that is not just trying to make sort of marginal gains in energy efficiency, but is thinking seriously about how we create a more affordable, more competitive Commonwealth. And I think you're going to see a great example of that tonight. I think that the work that Paul is presenting is really the start of an important shift in how we think about the value that Passive House and high performance building delivers, going beyond just the benefits to the occupants and thinking about the value that Passive House provides to developers, to utilities, to all ratepayers, to anyone interested in buying or renting a home, to everybody. And really thinking about that value and how we capture that is a critical issue, and one that I think Paul is very forward-thinking in addressing. So without any further ado, I'm very pleased to welcome to the stage Paul Ormond.
Thank you so much. Hi, terrific. Thank you for the nice intro. I really appreciate it. I just want to make sure you can hear me okay. Great. For those that don't know me, just for those that might be online, etc., my name is Paul, and I work for the Department of Energy Resources. We are the state energy office responsible for building decarbonization. What I'd like to talk about this afternoon or this evening, and thank you for making it out on this beautiful, beautiful night. I feel very special that you're here on such a beautiful weather day. I'd like to chat a little bit about our observations about how Passive House is a critical part of a critical foundation of making a more affordable energy infrastructure, a more affordable grid, and will also speed interconnection. And that relates to more housing faster. So if we want lower costs and more housing, Passive House is really the critical thing that we need to do.
I'm just going to get something that's weird on the screen.
Thank you. Thanks for your help. I appreciate it. And gotta click that, and then okay, there we go. So the kind of things it takes to make our grid more affordable, our energy more affordable, are really the ABCs. To go from 2 grids to 1 will make things more affordable. To avoid peaks in our grid, that will make things more affordable. and lower energy costs and to improve utilization. So about 60% of our energy cost is the cost of the wires and the cost of the pipes. So everything that you hear tonight would still make sense, even if our energy supply was free. So the key to affordability is not necessarily just more supply. It's these three things to make the cost of pipes and the cost of wires go down. So passive house is a critical element to unlocking a better strategy for those ABCs. So I'd like to just take a moment and take a look at where does Massachusetts stand in terms of passive house adoption and in terms of electrification. So we have a terrific program in Massachusetts called MEPA. And the reason this is so useful to look at is because these are projects that are being permitted today. It captures many medium and large size projects in the state of Massachusetts. So it represents a really good sample. But also these are projects that are going to be built in 2 to 5 years, sometimes 10 years. So when we look at what's being permitted through MEPA and the commitments being made as part of the MEPA process for these planned projects, we can get a good sense of what's coming, what's in the pipeline. So it's a forward-looking process. So we took a look back as far as 2020 so far. We're taking us back to 2018 right now. And we found that passive house adoption in Massachusetts in our leading indicator with MEPA is just unbelievably strong, and it's accelerating. So as of end of 2025, so we're already 6 months into 2026, we had almost 20,000 multifamily passive house units committed through the MEPA process. If we look at adoption rates of passive house, it's also very, very strong. So these adoption rates are it's the ratio of the number of multifamily units that are committing to passive house through the MEPA process divided by the total number of multifamily units in the MEPA process. So it's the adoption rate across all multifamily units in that process. And you can see amazing adoption rates that are 80% plus. So we had an adoption rate in 2024 of 81%. Now 2025 looks like it goes down, but if we filter that for just if we narrow that search to the multifamilies that are eligible for mass save incentives, that number goes up to 82%. So it's a real testament to the mass save program, I think, here developed by the utilities. One of the other intriguing things about this data is that it shows that most passive house in Massachusetts so far that has been committed to, that's coming, has been voluntary. So the blue are the projects that are in stretch code towns, and the orange is the projects that are in specialized code towns. So you can see most passive house is not mandatory. And I think that's a combination of the mass save incentive, but also this community of AEC firms that can really deliver passive house, explain what it is, and help deliver it smoothly. So I think that's really the result of many years' work by lots of professionals that are working on this. I'd like to also share some information that we got on the adoption of electrification. So in Massachusetts, we've had an amazing revolution of space heating electrification. So if you look at 2020, just 6 years ago now, 95% of all buildings that went through the MEPA process were fossil fuel space heated. 95%. And 5% were space heated with heat pumps. And that has completely flip-flopped in just a few years. We do have now almost 100% space heating with heat pumps in the state of Massachusetts for the projects that are being MEPA permitted. So it is an amazing progress from just a few years ago. So just a shout out to Katie, who is involved in many of these MEPA projects and making some of these big changes occur through the years. So there is a bit of a backlash. Perhaps you've experienced it. We experience it. There's a lot of people that are concerned that our electrification is going too far, too fast. And I think, it makes sense, right? You're like, all these like wave of electrification that's coming. Are we sure that this is not too much, too fast? And we want to make sure that we don't cause problems with, too much load on our electric grid. And one of the go-to solutions to solve that seeming problem is to continue to use gas. And that also is contributing to less slowdown or a slowdown of adoption of the specialized, because the specialized is where we have our electrification pathways. So what I'd like to do is unpack that a little bit and see what the reality is when we look at the interaction of new building construction onto our grid. So if I were to build a building to the IECC standard, and in this presentation here, I'll have some examples of the IECC standard, which is the standard across the nation. And it's also what would be required in our base code towns. So we'll talk about passive house, and then we'll also talk about what the standard would be if you were in just a stretch code town following what I call a thermal code. So we'll cover all the bases. So in the IECC standard case, if you were to build a building to that standard and to space heat it with gas, the y-axis there is showing the load on the gas and electric grid associated with space conditioning, whether that's heating or cooling. That's the y-axis. So an IECC building space heated with gas would put a load of 9.1, those units that you see there, load on the gas grid. And it would put 3.7 peak load on the electric grid in the summer for space cooling. Now doing the same building with passive house standard, but now switching from gas space heating to electric space heating, the load on the grid in the summer would be 3, and the load on the electric grid, not the gas grid anymore, would be 0.8. Okay, so let's hold that thought for a moment. Let's take a look at what our grid looks like. So this is the behavior of our electric and gas grids, the electric grid in red, the gas grid in green. And you can see each year going up and down, et cetera. Now you'll see that the y-axis is been made generic. And that's because this behavior, these shapes, and these are relatively correct to each other. Those shapes are in fact what you would experience if you were to look at this question for the entire nation of the US. They would have that same pattern, just different magnitude for any state. They would have that same pattern for any locality or municipality. So you can think of whatever scale you want with respect to this question, but the pattern would be the same. And the 3 things that you have to pay attention to, the 3 points, is the peak load in the winter on the gas grid. So that's 0.1. And then there's a peak load in the summer on the electric grid, and that is 0.3. And there's another smaller peak in the wintertime on the electric grid, and that is 0.2. So you have to kind of pay attention to those 3 points. And whether you're doing this at the national scale, a state scale, a regional scale, municipal scale, it is generally the case that the peak load that you experience in the winter there, that's the size of the gas grid in whatever sample size you're looking at. And the peak load in the summer for the electric grid is about the size of the electric grid in whatever sample you're looking at, again, whether it's nation, state, or city. So just isolating now 1 year and getting rid of those other multiple years. So just pay attention to those 3 points. And what I like to do is I have a new building. So I'm superimposing these peak loads on our grids, plural. So let's take the IECC heated with gas, right? The 9 and the 3.7. If we did that, what that requires that we do is that we expand the gas grid by 9.1 for the winter. And we have to expand the electric grid in the summer by 3.7. So that's the 2 peaks that you see there. So when we build with gas, if our go-to to save the electric grid is to build with gas, we see that that's not a great strategy, right? If we build with gas, we're having to expand two grids. Okay, so don't forget the gas grid in all this equation. Now let's go back to what we had for our passive house peaks and superimpose that. So that's what I have on the right side now. So now this is showing what's happening in the summer, just breaking this up a little bit. So what would happen is in the summer, I have to expand the electric grid to accommodate that summer growth by 3. But that number is smaller than the IECC built to gas. So already you're seeing that when we go from IECC gas to passive house all electric, the load on the electric grid that the expansion required is smaller. We're not doing ourselves any good by sticking with gas. Now what happens in the wintertime? In the wintertime, we're not expanding the gas grid because we're not using it. And we are expanding the electric grid in the wintertime a small amount, but that actually helps us because that's improving the utilization of the already existing electric grid. So we're using the electric grid already built for the summer, more in the winter. That's going to make costs go down. So now if we were to project the IECC gas strategy, this is what's being done in many parts of the US. If we were to project that thousands of buildings onto our grid, what would happen? We'd have a scenario that we call Twin Peaks. So we have to build our gas grid out significantly. We have to build our electric grid out significantly. We have 2 grids. The utilization of both grids is getting worse. So that's basically the maximum cost way to do things. So if you're looking for affordability, IECC with gas is not the right solution. Now, if we do the same projection, thousands of passive house, all electric space heating, what does that look like? The grid in the summer will go up. It'll go up by a smaller amount. So the growth on the electric grid will be smaller than it was in the other scenario. And then we're going to grow that use in the winter, which is, again, a good thing. And we're going to avoid growth of our gas grid. So how are we doing on our affordability ABCs? We see that Twin Peaks is no, no, no across the board. It is the least affordable way to do our grid and to approach affordability of energy. And passive house, ideal grid, is reading all of those strategies of ABC very nicely. Okay, so that's IECC with gas. That's the kind of go-to business as usual in many parts of the country. But we are seeing a new business as usual in many parts of the country as well. We do have a situation where the last few years there has been more sales of heat pumps for space heating than fossil fuels for space heating, if you look at all the national data. And that means that we have a new business as usual, which is standard IECC codes, but instead of using gas for space heating, we're using electric for space heating, sticking with the IECC code. And you see that you have a scenario that we have in the middle. And what happens there is that we have the same summer peak of 3.7, so that's again larger than the 3 for the passive house. We also have a huge, huge new winter peak. So we have a peak of 3.3 versus 0.8. So what happens if we take that and we look at other, this is now looking at other building types. So that ×4 larger winter peak for space heating is what you see for multifamily. For non-residential, it can be even worse. You can see if you look at the same stuff for the building use of schools, it can be almost ×10. So it's a really not great strategy if your goal is affordability. So if we take that new business as usual IECC with all electric and project that for thousands of buildings, we get grid maxing. So here we're growing our peak in the summer by a lot, and we're growing our peak in the winter by a lot. 2 huge new peaks in our electric grid. we're growing the winter peak sort of too much, right? We're going way past better utilization. We just have a whole new peak. Now, how does it do on our ABCs? Well, clearly not great on B and C because we're making worse utilization, we're increasing peaks. But even A, I'm going to gander that that's a maybe, because even though it may seem like we're building all electric with our IECC building because we're using heat pumps, I'm going to bet you lunch that it's the case that many owners, many designers would insist that my building built to IECC standards, we all know they're leaky, they have thermal bridges everywhere, don't even count those, and that in reality, everyone knows that it's a good practice with IECC buildings to have backup gas for those really cold days. So I would argue that even A is not achieved with an IECC all-electric strategy because we're going to, in the background, still have to grow our grid for, accommodating those 10 days a year. So that's even worse utilization than you can possibly imagine. That's sort of like maximum bad utilization. Okay, so we do have in Massachusetts a little different thing called the stretch code, which is IECC plus some stuff. So I want to show where that fits into this model here. What's different about the stretch code is that we have our 4 pillars. We include air leakage. That's at a much better rate than standard IECC, thermal bridge mitigation, ventilation, and envelope backstops. So those 4 things work together to deliver what we call the thermal code. So it's IECC plus those things deliver better performance, heating and cooling. And that lives in both our specialized and our stretch code levels. So if I were to look at what do the peak loads look like for different building types for our thermal code, which is in our stretch code associated with space heating, what you find is that we definitely do better. I'm looking at the top 2 rows now for residential buildings. We do better than straight IECC for sure by a factor of 2 because the mass thermal code load on the grid for heat pump heating is, quote, only ×2 worse than what you get with passive house. So it really validates why having a passive house mandate is a worthwhile thing for our specialized code. Now, the Massachusetts thermal code does do pretty well for non-residential buildings. So again, the specialized code doesn't mandate passive house for non-residential buildings. And I think these results justify why that's a sensible thing to do. So I think that shows nicely how the Massachusetts thermal code fits into this model. Okay. Are these peak demand loads very real? This is some really exciting new information that really validates that all this theoretical stuff I was showing is actually true. So this is a paper that was published just a few months ago in ASHRAE Journal, written by Stephen Winters Associates. And this is the result of years of work of monitoring passive house and non-passive house multifamily buildings in New York City, similar climate as ours. The blue, or the y-axis, is the thermal energy demand intensity of multifamily buildings. So it's for space heating. And the blue is that value for non-passive house, and the red is that value for passive house buildings. These are measured. This is not theory. Now, if we go and look at sort of design temps, the x-axis is outside air temperature. So if I go down there and I look at outside air temperature of about 10, what do I see? I see that the non-passive house has 4 times the thermal energy demand intensity as a passive house building. So it's a step change better to build with passive house than non-passive house. If I convert those y-axis units to load on grid, the numbers I would get would be 4 BTUs per hour per square foot and 1 BTUs per hour per square foot for our non-passive house and passive house scenarios. And then if I go back and take a look at my table here, my modeled passive house load on grid for heat pumps for passive house was 0.8 and 0.7. What was measured was 1. My modeled IECC was 3.3 and 3. What was measured was 4. So these modeled information has a lot of validation based on those many buildings measured over many years in a similar climate. Okay, so we've been talking about load on the grid associated with space heating, space cooling. The reason I did that is because that's the thing that's changing. When we have a thermal code, we make that smaller, we crush it. We're also changing from electric to gas space heating, gas to electric space heating in those scenarios. So that's why I'm focused on that. But the thing that the utilities care about as well is the overall load. So the load on the grid, the electric grid for all uses. So lighting, pumps, fans, et cetera, domestic hot water, et cetera. So let's take a look at and examining that for load on the grid. So if I were to, this is a real project. We had a building project that is building housing. This is located in Massachusetts. We're going to call it Project X. And Project X designed this whole project and then went for their grid interconnection work. And as part of that work, it was estimated that the load on the grid would be 11, the peak load that would occur in the winter. So then the implication then being that the grid in the area, the grid in the neighborhood needs to accommodate a load of 11. And normally we love going to 11. How many of you know this cultural reference? Raise your hand, you're my people. Thank you, Gen X. In this case, going to 11 is not a good thing because it turns out that this housing project was actually built to passive house standards, designed and built to passive house standards. And the peak loads that was estimated from that process were 2/3 smaller than the 11. And so this is something that the local utility, National Grid, was interested in. And they're looking at the landscape of this and thinking, if we have to build to 11, we have to upgrade all this stuff. It's going to cost a lot of money, but worse, it's going to take about a year for us to be able to interconnect your building. Now, if it's actually 3, we don't have to make all those upgrades, and it's going to take, a lot less time to make the interconnection. So National Grid has begun an amazing program of going out and measuring built, operating, occupied passive house buildings and non-passive house buildings. This shows the results of their 2 first measured passive house buildings that are in operation and looking at summer and winter peaks. That's building 1, building 2. And the measured stuff really validates the modeled stuff for the peak load. So this verified those model results, and it verified that the interconnection now can go much faster. So if you want more housing sooner, build to passive house. If you want to slow down housing, build to not passive house. And that's measured in the field and validated. I just want to take one more step into this because I think we can go even better. We can further accelerate housing production with passive house when we add demand response. So if we dive into and disaggregate that 3.2 and that 2.7, what do we see? If we disaggregate it, what we find is that 2/3 of the peak, the summer and the winter, is attributable to space heating or space cooling, depending on your season, and domestic hot water production. So we all know that if you live in a passive house, have a passive house, you can turn off the space heating, space cooling anytime in peak conditions, doesn't matter, and the occupants would have no idea that you just turn the heat, cool off for many hours, even days. So if you wanted to create a demand response program for a passive house, this would be a great thing to do, right? So we could turn the space heating off, the space cooling off at peak times and not disturb the occupants. Now couple that with demand response for water heating, which is the blue, which is something people have been working on for a while, that's adding storage. If you did that as a combination, you take out 2/3 of that peak load, bringing the peak load down to 1.1. So it's literally an order of magnitude smaller than the kind of peak loads that have been being estimated based on many years of building construction, et cetera. So we're entering a whole new era of how we can approach housing, how we can approach interconnection, and a way to accelerate housing that is critically needed now. So I'll stop there. Hopefully we have plenty of time for questions left, and I didn't go too long. So thank you for the opportunity to be here and share our results. Thank you.
We have enough miles. Thank you so much, Paul. And we've already got some questions, so we'll do some in here and then we'll go for some online as well.
Actually, two questions. The first question is, like we do a lot of like grid interaction for like commercial buildings, and like it's still even like passive house is helping with the peak, but it's still, I'm wondering if you can see that next step as like all of these multi-families are getting moved to passive housing, also can interact with the grid to lower their peak. And the second question is, which is something that I'm talking with, if you know Rosie in our team in the WSP in the office, we are trying to figure out if we can use the load calc with Woofy passive, because one big problem is the data, like despite other energy modeling tool, we can't really rely on the load calc and the EUI from Woofy passive. So that is because like you showed the measure data, which was fantastic, and that's something that like is going to convince the market, but it's still not helping me in the design to tell the owner that this is going to be the scenario. But thank you. If please ask one more.
Yeah, let me address the second question. I was having a hard time hearing the first, but we'll come back to that in a moment. So on the second one, you should really take a look at that ASHRAE paper that was done this past winter journal, because they talk about exactly that. They show that the Woofy peak, predicted peak, is too low. And that in order to so this and these results here, those 3.3, that 2.7, that's not what you get out of Woofy. What they did was they took Woofy and they fixed a too low assumption for water use and water use peaks, because that is sort of artificially low in Woofy, and they made it a realistic number. And then they calculated the average, the total, and they got that. So I think there's a fix that for Woofy for you to have a good representative, accurate picture of the peak that would also be consistent with measured peaks as well. And on your first question, I'm sorry, I missed it. If you can just repeat it briefly.
The question was pretty much like, how do you see grid interaction in passive house projects? That was the short of it. We know all the histories with commercial buildings, higher all those, but how do you see because again, this is something haunted in my mind as you were presenting, that it's already helping the peak load, but what if all of these passive house projects also interact with the grid to lower their demand when the grid is already at the peak?
Yeah, I think it's really important for us to, this is why I wanted to turn the conversation to peak loads. We always have these conversations about, total annuals, and which makes sense because we want those to be low. And then we turn the conversation to, heating, cooling demand, which also makes sense but that is an aggregate, that is an over time measure. And that's why I think we also need to turn to, so we can sort of justify passive house based on how much less energy it uses, how much less demand there is, better comfort, all that kind of stuff. But we have to add a new dimension to why the value of passive house, which is the peak loads. And that's what I'm trying to do here and introduce that. So I think as practitioners, we need to start having conversations about the peak load that you're getting in your passive house, and to estimate what would the peak load have been if it wasn't passive house, and show both numbers to planners and estimators in the world, because we also have to actually differentiate between what it takes to grow our grid because we're just growing, because we're adding more housing, because we're adding more. So there's going to be growth of grid because we're just growing. And we have to differentiate that from you know, that we're doing that in the smallest possible way with our passive house strategies. And if we weren't using passive house strategy, the growth on the grid would be so much bigger. So I think that's how you always have to frame it.
I'm looking at this graphic on the screen right now, and when you talk about an old school sizing of 11 versus a modeled sizing of, let's say, 3.2, the delta between those, in a way, it represents risk, right? Someone has to decide that they're gonna not size it to 11, they're gonna size it to 3.2. And someone's gonna have to assume a risk by doing that. So coming from a design firm, well, we don't want to be the ones to take that risk. Are we going to advise our clients to take that risk? What's the incentive for anyone to take on that risk when, even if it's sized to 11, they're only actually going to use 3.2? You know what I mean? So we find ourselves oversizing so that we're not on the hook down the road when it's undersized potentially. So there's a dilemma there.
Yeah, that's a great point. And I think there's a lot more that can be done to bring designers kind of from this direction, this way, and bring utilities from here and bring them this way and meet in the middle. One of the things that we need to remember about the grid is that there's diversity. So within a grid, if you build a bunch of multifamilies and you build a bunch of office buildings and you have a bunch of existing load, it is true that you can calculate peak loads on all these different buildings to be X. But it is in fact the case that there's the sum of them isn't the sum of all the X's, that there's diversity, that some of those buildings are going to be used less at that moment and some of the buildings are going to be used more at the moment. And so it isn't an absolute thing that you have to be correct on the 3.2. You just have to be correct on the 3.2 most of the time. And so that's how the grid designers think. So that's why we have to kind of bring grid designers this way, we have to bring HVAC, MEP designers this way and meet in the middle. And I think National Grid, we've been talking to them about these results. They seem super excited and interested in this because their interest is to speed up interconnections. They don't want projects to be slowed down because we're trying to build to 11 when it's actually much smaller. And if you're worried about the 3.2, well, then make it 4, but it's not 11. So that's just some thoughts on that. That's a great question.
And I'm just gonna follow on. And is it not the case that the 11, that's a decision by the utility, right? The utility is saying what? Are they not making that determination?
I think it's both. That's a process that I'm not familiar with. It's not my day-to-day work. I think the utilities rely on what the designers say to some extent and their standards, and then they also do their own diligence. And at the end of the day, where they land and how they land that's a good question. That's why I think we need to kind of get the people in the room and meet in the middle.
Signal from the line.
This is a really easy one. Back from the beginning of your presentation, somebody was asking for clarifications about the metrics for number of dwelling units. Are they per year or cumulative?
Okay, let's go back.
It was before the electrification horror slide. Yeah.
So that is cumulative dwelling units. So this is showing that in the year 2020, there were about 2,000 dwelling units that committed to passive house when they were permitted in 2020. And then in 2021, there was an additional 1,000 or so. So it went up 1,000. And then in 2022, it went up another 3,000. So this is them added. This is a cumulative plot. So today we're at about 20,000.
Can you go back to the 11 and slide and we're on for a little bit.
With the 3 pairs?
Yeah, we tested once. But this is question, but also a challenge, just for the room a little bit, is from an HVAC equipment side of things, is you build these passive house buildings, and what you're showing here are the loads, but the actual connection to the building has to be a little bit of the sum of the equipment and the nameplates, and as many of you know, there's issues with how small equipment goes, especially in Massachusetts with 1-to-1, how small a single compressor can go. There's improvements there, but until we can centralize systems and take diversity of 20 suites on one system into account, we're really missing out on an advantage there of how to size things. It's just an independent hydronic fan coil, if you're a fan coil, you can size that really small and have an economy of scale on compressors. So even that building at 3.2, the nameplate of everything in the building would be higher than that, and that becomes a challenge. And of course, our limitation is tenant building rules with central systems. And we're trying to convince, talk to developers about, you can still centralize it, put it in the rent, beat the market that way. That's one of the big barriers here. And we're pushing our manufacturers to get smaller equipment, but the 1-to-1, it's only gonna get so small, especially with heights of buildings. More of a challenge, hope the ideas, but really try to push for central systems.
Yeah, there's a real, there's a parallel there, because for decades now, as passive house people, looking at, some of the designers have been doing this for a long time, there has been this tension, because the loads are very small, like you're focused on your building, and the loads are very small, but the equipment sizing is not caught up with the idea that it's small now. Maybe because the equipment doesn't exist, might not be that small. But also in general, like we know that our HVAC equipment sizes can be downsized, right? And within some limitations, and so there's been tension there, and people have been working on this for a long time. Well, we're in generation 2 of this, where now the tension is like, when you aggregate all these things, when you put them together in a building, now we're going to have a load on a grid. And now it's the same thing. We're re-examining kind of the rules of thumb that were used to size grid, and showing like it can be much smaller than the rules of thumb used to be. Just like there used to be rules of thumb for like how big your fan coil units need to be. It's like so many fan coil units per square foot, right? So then you got this size, and you're like, wait a second, this is a passive house. There's going to be way smaller. So it's like there's a parallel there, which I think is interesting.
All right, another question online from Tom Phillips in Davis, California. About the life cycle analysis, what do seasonal peak loads look like when climate shifts to more cooling demand and less heating over this century? Assuming current building code versus passive versus climate ready.
Yeah, so the question, it sounds like, is how do these dynamics play out when there's more need for cooling than there is now? Now, and I would argue that the heating doesn't necessarily go down. This is a peak. It only has to happen once. So I wouldn't say that peak heating necessarily goes down, but I see going into the future, I think the cooling could actually increase. I think all the more reason to use passive house as opposed to IECC standards, because the passive house will be way less susceptible to overheating than an IECC building. So all the more reason to have demand response, all the more reason to be prepared for that, because we could literally turn the cooling off during the worst of the peaks and help our grid, and the occupants would be fine.
Okay. I'm asking, there's a demand response question. I was asking what we're on that. So one person, Pete Russ from HMFH Architects, wondered if you could explain a little bit more about demand response. How would you turn off hot water or space heating / cooling at peak times without tenants being affected?
Yeah, we'll go back to this so we can see visually here the benefit. Yeah, I mean, what we're doing here, so in a passive house, you can turn the space heating off, and the occupants simply wouldn't know for probably a day or so during the coldest day. Or you could turn the cooling off in a passive house, and the occupants wouldn't know for at least a day or so. So you could easily turn those off for 2 to 4 hours during peak times, and the occupants would have no idea. And this is the same kind of program that we've been using for decades with lighting. So the utility is connected to your lighting, and the utility actually turns the lights off for you. So in a supermarket, for example, they have 10 bays of lights, and during a demand response event, they turn off every other bay. So there's still light in there, it's just not as much. And that's done for 2 hours, and the building owner has, the building owner is not doing this, the utility is doing this when they need to, and the building owner is then being paid for providing that, ability of the utility to not have to run such high loads. That's how we do it. So on the thermal side, you only do this with passive house. You definitely don't want to build an ICC building and turn your heating cooling off, and that people are definitely going to know it's going to get cold or hot fast. But this can be done in a passive house. So passive house opens up new opportunities for demand response that are enormous. That really, I think we need to all put our shoulders to and consider when we size our utilities. For hot water, it's actually fairly easy, right? It's just create the hot water, store it in a tank, and then use only the water from the tank from 2 to 4 p.m. And that's how the users don't know. So the occupants have no idea the demand response is happening in the background.
I just want to go back to Katie's question on design, because I had similar experiences designing the sizes to the MEP, and the guy is not gonna sign it because it's a liability issue. It's a liability issue, they don't want to get sued. So I just want to go back to the question I had, that one thing that I figured, I'm curious to know what you all think, is it's the issue of methodology. So like two things is like, one, we are already dealing with the future data on the climate fund, it's getting hotter or warmer, and we're at the question on the shifting. So using the future climate funds to better understand the peaks and use another tool than multi-passive like IES or EQUS, or to do the load count, because I have the same find that like the MEP want to go to train trace load count and top it with 30% and then size it and put my work in trash, because they're like, because oversizing is gonna kill all of our saving and all of that problem. So that's, I think, the issue of the liability could be saved with the better methodology, like run another model like parallel to your multi-passive, or reference to that article that we mentioned when we look into that. But that I think is gonna help us, because like I'm also dealing with the same issue. Like if I do a little work and at the end, the engineer of the record needs to be comfortable to sign, and they won't.
Yeah, this is why National Grid and other utilities are really interested in measuring all these things, because these models are just like, go around in circles after a while. But if you measure it, you have like, dozens of buildings measured, you can have a very high confidence that instead of being 11, it's, you depend on how much you want to sharpen the pencil, maybe go to 4. It doesn't have to be 3.2. But that's not 11. So that's why measuring it is so critical. We haven't really been great as an industry at building science people to really measure things. There's like not a lot of feedback loops. And there really hasn't been a need to, like, it's been like, I got my lead model, I show my code compliance, and that's just all built on models, so done. But now that we're talking about investing, hundreds of billions of dollars in our grid across the nation, probably a good idea to start measuring how our buildings do, and then we can design our grid growth more leanly, right, based on actual data and not models. And I think that's why this measured building 1, building 2 is that's a harbinger of what's to come, I think, for the direction that we want to go.
John Gregory Lakeville has, I think, a terrific question. What is the economic advantage to the developer for faster interconnection? And has that been quantified in any way?
Well, it's the old adage, time is money. The economic advantage is you get your building up faster. And I think that it's usually the case that a developer assumes a certain, certificate of occupancy date, right? And that's built on the assumption that the grid interconnection goes smoothly. And what we're seeing in many cases is that the grid interconnection comes in, it's like, whoa, it's gonna be 1 year delay. I mean, it's just like telling a developer that, you know, your project, instead of being open in 2026, is gonna be open in 2027. So it's significant financial penalties to the developer. So I'd like to see a world where if you build to passive house, you know, you're given sort of the front of the line for a grid interconnection. Where, you know, the utilities are like, built a passive house is great, put DR in if you want, but we know it's gonna be a 3, it's not gonna be 11. It's a predictable thing for us. We've measured it a bunch of times, we know what to expect, that passive house get great quality assurance. So we know what we're getting, so we're gonna be able to put those buildings on quickly. And if you agree to passive house, you're front of the line. If you're not passive house, it's gonna be a little bit more, we're gonna be a little more careful about it, because we don't really know that it's gonna necessarily be 3, it might be 11.
That tees up my question perfectly, which is, all right, you know, you've laid out this great path, this argument for what you just said, for accelerated interconnection with appropriate safeguards for the fact that the models aren't gonna be perfect, you know, assuming we've got, you know, good data. How do we get to that world? What does DOER need to do? What do utilities need to do? What does BH Mass need to do? How do we get from today, where it looks like this is possible, to a world where, as you suggest, passive house could be at the front of the line?
Yeah. I hate to volunteer myself for stuff, but I'll probably end up doing so in the course of this, but I think we need to, as building people, start daylighting and putting a much bigger priority on identifying peak loads, identifying what they could have been and what they are, conversations early with utilities to have, you know, to talk about interconnection and how much lower this would be versus that. So that's something that we can sort of all do in our day-to-day. But I think kind of like programmatically, you know, I think we need to, like, you know, systematically start, let's measure 100 buildings and let's share the information. Let's get some sort of like database or some, you know, singular point of contact for all these measurements and all these modeled information, and keep, you know, validating what these are, so we have more and more confidence to go forward. And let's just keep this cycle going to, you know, keep reinforcing why we need passive house in the code, keep reinforcing why the specialized is so important, keep reinforcing why mass save is so important. And then I keep bringing this back down to, this makes things more affordable, and this lowers the cost of energy, and this makes housing go faster. So I think we just keep that message out with everywhere out there. And I think that's gonna be, you know, the way that we get to that promised land.
Do you have any other questions from the room? Oh, yes, Maura. And I volunteer PH Mass to
Great.
Just to build on what you were saying before, and to kind of connect DOER programs, so do you see LBER being a big piece of this, actually getting measured data on these buildings? Because theoretically, there's already a system in place to do this, and how do we prioritize getting good data on those passive house projects, maybe first and foremost?
Yeah, that's an excellent example of, like, you know, kind of getting out of our silos and like seeing how we can use information being collected for one purpose for another purpose. But absolutely, if you LBIR are going to be measuring buildings that are now put in service, those are going to include passive house buildings. And they're going to include non-passive house buildings too. And we need, if we can take that information and systematically put those side by side, and then show this is why passive house is so important for our grid for affordability, then I think we have a winning thing. So yeah, doing all of the stuff related to measuring, you know, the measurements that are done with that program, I think can contribute to this conversation.
Certain buildings, National Grid can provide that data. Wait, no, I'm sorry.
Sorry, Sean.
Yeah, the utilities can provide that depending on the type of building, and maybe that becomes the checkbox, you know, can they provide it? And if not, maybe the first year there's some measurement.
Yeah, yeah. The utilities are, I don't know all the details. They're unrolling all the smart meters, but there's so much more being built out there that allows measurement of data, measurement of peak loads, 50-minute intervals, all that kind of stuff. And, you know, I know the utilities can't share like publicly information in any old way, but certainly they could categorize information, can know that a building, you know, this is a building heated this way, cooled that way, space, water heated this way, falls in this category, here's the peak loads, you know, and then just kind of accumulate all that information, share with everyone. That would be great.
All right, well, we've come to time here. Can we have a big round of applause for Paul Ormond?
Thank you.